everyone. I'm Cédric. I am working with JuliaHub, but this talk will not be about anything I do with them. This is about one of my personal projects in the graphics programming realm that I feel has been somewhat underexplored in Julia. Besides all of the plotting ecosystem, there are lots of cool things we can do with graphics. And I'm going to give a talk about, thank you, about Vulkan, which is a way to interface with the GPU. It's essentially a graphics driver. So I'm going to make a small introduction to Vulkan and then to present how I made Vulkan.jl so that we can interface with it in a safe, correct, and easy way from Julia. First, I'd like to have a gauge. How many people have heard of Vulkan or have a rough idea what Vulkan might be? Okay, I guess a third, but we're not so many. So first off, I'd like to address something is that we have in the Julia ecosystem, in the Julia API GPU ecosystem, we have a lot of packages to do compute on the GPU. Things that use CUDA or the equivalent from AMD or OpenCL. This is most of what you will find in the Julia GPU stack is to support this compute use case. What I want to do is actually graphics. So you can think of OpenGL or Vulkan in this case, which is about using the GPU to leverage the graphics specific hardware functionality that makes a lot of the rendering fast. You can think of the rasterization process that you want to do when you render something on screen. Say you have a bunch of triangles, you want to do some raster operation to figure out which pixels of your image are covered by these triangles. This is something that is very, very fast with specialized hardware circuits. And you also have, for example, ray tracing that we can do with the graphics driver that can be replicated in the compute world, but usually will be so much slower. Or at least the intended use case for graphics is to target things like games or high-performance 3D applications or these kinds of things that are very, very demanding, specifically to display something. So, to quickly mention Vulkan, so it is a graphics API to interact with the GPU. I'm not saying a graphics library on purpose because it is actually just a specification, or just. It is a document that specifies what the API is, how it should behave, but there is no single Vulkan library. It's the same thing for OpenGL, and essentially it is up to every hardware vendor to implement a library, for example, a libvulkan.so, that then they will have available as part of the OS in a way that is conformant with the specification, with the behavior that is prescribed in the Vulkan specification. So OpenGL and Vulkan are two of the graphics APIs. There are others, but I notably covered these two, and in particular Vulkan, those from the Kronos group, because they are cross-platform and vendor agnostic. I mean, it will work on Windows, AMD, will work on Linux, NVIDIA, for example. And the developer should not have to care about. So I don't have a replica on my laptop, but I'll just log in there. All right. So as I was mentioning, Vulkan is essentially a specification that will be then implemented by hardware vendors like NVIDIA or AMD, so that then they can ship a driver that performs what the Vulkan specification dictates in terms of API and in terms of behavior. They have conformance tests. Kronos has conformance tests to make sure that the behavior is indeed correct, and that the developer can use the API regardless of the vendor. So just to quickly mention, you might want to use OpenGL still, even though Vulkan is more recent. The reason for that is that OpenGL is easier to use because it is somewhat of a higher level API. With Vulkan, it is great because it is very, very low level API. Everything is explicit, but everything is very verbose. The driver will do exactly what you say, what you tell it to do. Whereas for OpenGL, it tries to do some guesswork to figure out, okay, what do you probably want to do on the GPU? The inconvenience for OpenGL is that if you are using it as the foundation for a renderer framework or library, then you might lack clarity over exactly what operations are happening on the GPU, what state are you in. Notably, it uses global states, which is a bit harder to reason about. But if you want to just do some graphics very quickly without diving too deep into how GPUs work and how Vulkan works. You should definitely use OpenGL. But I will be covering Vulkan notably because I think it might be a really great foundational layer on which you can build a lot of Julia libraries that will essentially support a lot of things that you want to do on the GPU. So as I mentioned, Vulkan is very low level, very explicit, very verbose. One disadvantage of this is that you will not want to just perform a series of calls to the Vulkan API to get your work done. What you want to have are abstractions. Notably, it takes like a lot of lines to render just a simple hello triangle, which is like more than 1,000 lines in Vulkan. In OpenGL, it would be much easier. In OpenGL, it would be much easier, yeah. So what you would want to have is instead having Vulkan as the low-level thing you interface with, and then build a renderer library on top of it, and then this is what your application will interface with. Application or script or anything that you like that wants to use Vulkan to render some graphics. So now let's talk about the Vulkan interface from Julia, because it might seem like oh, lost signal again.
Okay. Okay, this time I might be able to do that. Oh, yeah, my bad.
Okay. And this one gets here. Okay. Do you see all of the? Do you see until the bottom? Okay, then I think I'll just stay with this if that works. All right. So when you interface with Vulkan, you interface with a shared library, a driver, which is a .so. And so it's typically a C interface, and you'll do everything thinking about C interop. Chronos provides a set of Vulkan C headers that you can use with Clang.jl, for example, that you can parse with Clang.jl to generate a bunch of functions and types on the Julia side. And this is what the Vulkan core package provides. But we're actually far from finished there. Note, for example, in the structure, this VK instance create info structure, we have quite a few fields that are pointers. And that's going to cause a lot of issues. Because in Julia, when you have a pointer, it's just like an unsigned integer. You don't have an explicit reference to the memory it points to. Which means that sometimes you may take the pointer of an object, but that object may be GC'd away because the program does not know that with this pointer, you're going to access the memory of that object. And a somewhat trickier one is that sometimes the compiler will even not store things that you will not set the memory to a value that you would initially want to set. It would just elide some stores. Here is an example of that in action, where I have a function that creates a ref, and then I take the pointer of that ref, and I just return the pointer, and then we'll try to load from it. Note that we store a 0 in the ref, so then when we do unsafe load of the pointer, we should be getting 0. But we do get some garbage value. And the reason for this is that we actually don't emit any instructions that will store 0 to that memory. If you take a look at the LLVM code, there are not so many lines, but the most important one is that we do an allocate on the ref. We don't heap allocate it via the GC. It's just going to be a temporary allocation, and we just never store 0. It's just not in there. So of course, when we try to get the int at this memory location, we get some garbage value, or the value that happened to be there. So when you interrupt with C, usually if you have to generate pointers as part of a C call, that's fine. For example, if you perform a C call and you have a ref, and your CA interface expects a pointer, then Julia will call unsafe convert, like C convert, and then unsafe converts on that ref, which will turn it into a pointer, and the SQL semantics will preserve the object that you pass into it during the duration of that call. But if you have to handle pointers outside of a SQL, then things get a lot more dicey. And this is the case here with the structure where you have to store pointers in that structure. So the best solution that I thought of was to actually store pointers, to store the memory dependencies alongside the pointer or the structure that will contain the pointers. And this is what Vulkan.jl will emit as some kind of intermediate structure, just to guarantee correctness. It's a structure that has the ABI compatible C structure. Oh, shoot.
Geil. In?
Species on the
Yeah.
test.
So that, yeah. If someone could prep another computer also, that could be helpful, maybe. Yeah, because it seems like the bug is in all parts. All right. Or yeah, it's enabled. It's in very small resolution and a bit weird. What if we try this? Oh, just not connecting. All right. Oh, okay. That's good now. All right. Let's really hope that it stays. Oh, okay. So I don't have to relaunch that slide. All right. Let's just proceed from there. So one of the structures that Vulkan.jl will have internally is this intermediate structure that contains the memory that has the pointers and also all the memory dependencies for each of these pointers. So that in this case, we bundle the pointer and the memory they point to, so we don't, so we make sure that the memory will still be available so long as you have the pointers and vice versa. So the way that we do it in Vulkan.jl is then we'll generate a lot of code that generates all of these intermediate structures and also higher level structures that I'll cover in a minute, and a set of functions, but all that leveraging the specification. I mentioned that Vulkan is a specification, and that's actually fantastic because they provide a specification in XML format, which we can parse and then understand what's going on. This is a small example from the specification. And I made a package called Vulkan spec that can just parse the specification and then introspect into the structs and functions it has. In particular, you'll notice that it has like almost 1,400 types and more than 600 functions. I don't want to do this by hand. Now, with this information from the specification, we can generate a few data structures. So there's the intermediate one that I mentioned on the top right. And on the bottom right, we have a higher level structure that actually contains vectors. Note, for instance, in the low-level structure on the left, you have counts and pointers, which semantically are arrays, but that's the C way of saying we have an array is just a pointer and a size, but we can actually manipulate vectors in Julia and then have things convert automatically when we need to interrupt with C. And then we have a bunch of constructors, which take into account optional parameters because the spec says that they're optional and so on. So there are quite a few cool things we can do. Now, how do we use it in practice? Well, you can just use the Vulkan.jl package, and then you just create your structures. So here we have some application info and some instance that we create. Those are just Vulkan-specific things that we manipulate. Whereas if you actually were to interface correctly with Vulkan, without this wrapper, you would have to write all of this code. A lot of code that converts things to pointers. We have actually an array of pointers in an intermediate step that we then take the pointer to, and we need to have the proper gc.add preserve. This is a lot of manual work. Compared with what we have here, this is just, okay, Vulkan semantics. Here we have to deal just with how to interface with C in a safe way. And that's what I want to take away, or to remove, is the necessity to think about these low-level details. So I'm going to quickly show some code that does something a bit more elaborate. I'm going to go quickly on this because I don't have a lot of time. Just don't pay attention to all the details. The important is the global picture. So the first block does some initialization on the Vulkan side. Then we essentially open a command buffer on the GPU, like for the GPU, that can record a bunch of commands that we want the GPU to execute. Then we close it, and we just submit that to the device and wait until it is finished. Just note here, the only thing to observe here is that we don't deal with pointers or cinterrupt at all. We just use a high-level interface. And it actually works. It doesn't crash. But if you compare it to this, you see it's like almost the same amount of code, but this one just does the first 3 lines of that one. But it does all of the cinterrupt. So I would say that's a big win to remove all of these necessary steps that are just happen to be done automatically from Vulkan.jl and in a safe way. All right, I'm almost at the end. So now let's show a few example renders that you can do with Vulkan. Note that you can do essentially anything with Vulkan using Vulkan.jl. It's just that I happen to have some examples to show you. So there's the hello world triangle that takes 1,300 lines of code in Vulkan that we can easily replicate in Julia. With much fewer lines of code because we don't need to do all of the cinterrupt and so on. And we have a high-level interface. We have also maybe some image rendering and some blurring using a compute shader. We can also render glyphs and then multiple glyphs for different fonts, different languages. And also we can render, for example, a bunch of glyphs, but arranged in a certain way to perform a sentence, to have a sentence. This one uses a lot of styling over the text and uses style strings to do so, which greatly facilitates annotating parts of the string with specific style information. There's some image of an erosion simulation going on the left, not the final state, but some intermediate state, and then some environment rendering on the right, where we have, for example, an environment image, either as a cube map or as a queer rectangular image. Like a cube map being a set of 6 images for each of the faces of a cube that represents all possible directions in 3D space. And a queer rectangular is a single image, but that has longitude and latitude coordinates, essentially. But really, you can do anything you want with it. There are no limits, really, and if you find limits, it's a bug. File this in Vulkan, and I will be happily fixing that for you. One small detail I want to add before we end is that okay, you interact with Vulkan from the Julia side, but eventually when you want to specify the shaders that your GPU will want to execute, the equivalent of kernels, but in the graphics domain, you typically, if you use Vulkan, you typically use GLSL, which is the same language as OpenGL. It's just that we compile it to a different intermediate representation, which is called SPIR-V, which is the equivalent of LLVM IR, if you will, but for Vulkan and also OpenCL. But how about we generate this from Julia? And it turns out that we can actually do so. I mean, we do so on the compute stack with the GPU compiler, so why not do that for Vulkan and SPIR-V on the graphics side? And so this is what the SPIR-V.jl package does, to be registered soon, but it's already in a pretty good state. I just need a lot more example like use cases that will surface all of the bugs that probably crawl underneath. But I've been using it for quite a while now, and it works well. And this is an example of a shader that gets generated with SPIR-V, which, well, just a bunch of SPIR-V IR printed with colors. All right. So just as a quick recap, we have Vulkan, that is a specification that will dictate how your GPU should implement the graphics driver in a cross-platform and vendor-agnostic way, so that then the programmer can use it without having to care about these details. Interoperability is very tricky to get right, but hopefully, well, fortunately, we can automate most of this away with Vulkan, with Vulkan.jl, leveraging the specification format that allows us to introspect into all of how the API works, how it is structured, which saves us a tremendous amount of effort and time. All right, thank you for your attention. Any questions?
Anyone have any question?
I can repeat the question just on the side.
You explain the advantage of this version Julia integration with Vulkan, like compared to any other integration with an API. But I expect there are some other interfaces for Vulkan from other.
So the question is about what changes from when we interface with SPURV on the Julia side as opposed to how we do it on the other Julia GPU ecosystem. Is that it?
Integration with Vulkan.
Yes.
Well, from other LEs. So I mean,
Oh, from languages that are not Julia.
integration of Vulkan in Julia, and I wonder if there's any advantage of this implementation over other integrations.
Oh, yeah. Okay. So the question is about we do this integration in Julia. There are other integrations in other languages. What are advantages of this wrapper in Julia compared to, for example, how Rust interfaces with Vulkan? The main advantage I would say is that we use Julia, which is a fairly high-level language. And for that, I made a lot of work to make sure that we get a wrapper that gets us also a high-level API. So I'm going to go back to my main example here. This is not something you would do in Rust. In Rust, you would allocate your variables and set a bunch of fields, and then perform a bunch of manual calls to manual IPA calls, and then check for status codes, things like that. And a lot of this is automated away here. For example, there are a few patterns that were automated that are quite low level that we don't really want to deal with in Julia. One of them, for example, is that most of the time Vulkan fills in some pointer that you give it or some ref that you give it, and then returns a status code as part of an API call. Then you have to check the status code, and then to actually get the semantically returned object from the call, you would just dereference the pointer that you created just for that purpose. Well, here we can just have result types.jl, for example, to wrap a call to Vulkan. That indicates that we can unwrap or check if we have an error or not. And also we just semantically return an instance. For example here, in this manual example, we do have to construct a ref to a VK instance, then call VK create instance towards the end, and then dereference the ref. So that's just all automated away here. You call create instance, which is another high-level function provided by Vulkan, and it returns you an instance. Doesn't return you, it doesn't fill in any pointer semantically. Any other questions?
Have you explored shipping also Vulkan's runtime on the ICD drive or any national drivers?
So the question is about have I explored any shipping of Vulkan or the Vulkan runtime as JLs? Yeah, I explored it with. I did actually some work to have Swift shader, which is a CPU implementation of Vulkan made by Google. So I compiled it with Binary Builder for Linux and maybe macOS, but not Windows, because there were a lot of issues. Or unless I just used the tarables and did not compile it. I don't remember exactly, but yes, I did explore that, which is very, very useful for testing, so that then you can just grab and implement a CPU implementation of Vulkan from Binary Builder as a JLL and use that in your test suite. You don't need an actual GPU to run Vulkan tests on CI.
Any other questions from the audience? I have a small question.
Yeah.
Among all your parameters, is there anything, I mean, I assume so, but that controls the quality of the image? I assume so, or not? Yeah.
So you mentioned...
Is it like easy to change? I don't know, you want to render like a more quality image or not, or?
Yeah, so for example, if you want to change the quality of an image, you might just change the resolution, and that's just a single parameter that you have to change in your Vulkan code. That's quite easy. Now, if you want to enable a bunch of render options, like whether you want to do multi-sampling or not, and also in the shaders themselves, it's actually, from the Vulkan side, it's actually fairly easy. If you want to expose it from an application side, you have to rebuild a bunch of structures, and it might actually be a tiny bit of a challenge, but it is something that is very explicit in Vulkan, so it's not surprising behavior, just potentially some more manual work depending on how you want to expose these parameters.
Okay. Well, let's thank the speaker again, even with all the technical issues. Thank you very much, and round of applause.